Hello everyone. Alright, so now I would like to demonstrate to you the steps on how we can get the expressions of H field due to other structure. So for this case, I'm going to use example or questions given for this test 2, 18-19 semester 2, question number 2, part A. So you can refer to that question set. For this question, actually we are given a circular disc with an inner radius of A and the outer radius of B with uniform surface charge density rho or rho s, the same thing, which rotates at its own axis, let's say in positive v directions, with angular speed radius per second. Okay, and then we are going to prove or to show that the H expression actually is equal to the half rho omega B minus A. So we have to find the H field at where? At the center of the disc. So this is going to be our point of interest, right? Okay, since this is a finite structure, so we can use again BSL, Biot-Savart law, to find the H field. Okay, let's do it together. From equation of BSL, the DH here, J S ds cos r vector over 4 pi r cube. Now my questions, how do I know that this element is going to be the JS ds, not IDL or not JDV? Okay, before that, before we go further, let me recall. Okay, let us recall to the last lecture which we talk about the convection current density. So as shown here, the J is equal to rho V U, right? From this equation of convection current density, we know that when any charge, this is charge, right? When any charge that move with constant velocity, they actually will produce a current. But depending on the charge here, let's say the charge is a volume charge, you will have here volume current density. If here actually we have a surface charge that move, again we're gonna have a surface current density. So for this case, guys, we have a rho s, a rho here, that move with constant velocity. For this case, a constant angular velocity, right? So we also will have a current, but this case become surface current density. That's why I'm gonna put here become the element of surface current. That's why you can use here for the J, in the case of rho s or rho, which move with velocity, you can have a JS, alright? That's why we have here JS ds. So before that, we need to convert this U into the omega. So how do we do? Right, the JS, guys, can actually convert in this form, the rho, the U, guys, here we get R omega phi, alright? Because we know that the omega, guys, rotating positive phi, so we can convert the U to the omega, actually become R omega phi. Okay, so we can have the final equations of this case will become rho R omega phi. That's your JS. So let's put this value into this BSL equation. You can have here the DH, right? So the JS become rho R omega phi. And now how about the ds? Okay, again, for this case we can do the same process, which have to take a sample or the current element. Let's say this is my current element that can be taken anywhere along the disc. This current element can be taken anywhere along the disc, which ranging from A to B or 0 phi to 2 pi phi. Okay, so that's the condition that must be met to take a current element. So that's our current element, which is Js ds. So for this case, I will know that the Js here, guys, actually depending on two parameters, which is r and phi. Alright, the z become constant because at 0. So ds here actually only refer to the two parameters, which is r and phi. So we can simply convert this ds, become Js r dr d phi. Right? So let's put that value or that equation to this BSL equations. You're going to have here the r dr d phi, and now turn to the r vector. Again, guys, the r vector actually the vector that joining from current element to the point of interest. So in this case, you are going to have this is your r vector only. Okay, we can simply say that the r vector here, guys, only composed of r component, which is negative r direction. Why negative? Because readily inward, always from sample or element to the point of interest. And why I put r? Because, guys, this case the sample could be anywhere between a and b. So you cannot put a, you cannot put b. So you must put a variable to make it valid. So here is negative r component. So here can I have here negative r component only, and then over 4 pi r cube, which is the magnitude of this vector, which is r, right? So that's our equation of BSL so far. So now let's do the cross product between phi and r. What will you have? The phi and r will have a negative z. Alright, so negative times negative going to have a positive one. So here we're going to have a positive z, and then let's multiply the r here with r here with r there, so we're going to have r cube altogether. So r cube omega, and also dr d phi over 4 pi r cube. So now we can simply delete this r cube because they are same. So what left you're going to have here finally with rho z rho omega. And now let's do dr d phi over 4 pi. Now let's do it the integrations. So the h that actually appear at the center of the disk can be obtained by simply integrating the whole term or the whole equations over r and phi, because we know that the r and phi is the two main parameters that involved in this case. So z, rho, omega, 4 pi, they are all constants, so take it out from the integration part. Rho, omega, over 4 pi. Now integrate over phi from 0 to 2 pi, and also integrate over r from where, guys? From a to b. So after you integrate this equation, you're gonna have this final equation shown as z component rho omega over 2 b minus a ampere per meter. So that's going to be our result for this rotating charge disk. So I hope you can try yourself and make sure you get same answer. And if you have anything to ask me, so just leave a comment on the channel, right? Thank you and all the best.